What I'm going to do is try to put it on the board. If you have questions, ask it. If you look, the solution should be up there on OneNote. Anybody confirm that?
They are.
All right. So I put them up there so you could look. Unfortunately, the Smith chart on that is not. It's not very good, but the equations and stuff, everything else is fine. So let me go ahead and start this. Is this somebody's coat? What? All right, so we'll go through it. So problem one, this is the stub tuning, and I did not give you a bounce diagram because I frankly don't think you would have had time right there. That's the only thing I kind of omitted. But for problem one, you have a transmission line with a load. And I ask you to match it with an open-ended stub. So this is going to be an open. And I'll just call that L stub. And this is L through. And let's see, the characteristic impedance is 50 ohms, right? And what was the load impedance, guys? Pardon?
25 plus 890.
All right, so now to go through this, I asked you to minimize the length of the stub. We could have minimized the length of the through line. This is length of the stub. So the first thing you have to do is always, and I looked for this, when I don't see this, I don't know exactly what to do because I'm at loss. There should be a normalized load impedance. So you should get ZL equals capital ZL over Z naught. When you do this, you're going to get 0.25 plus J, and this should be 1.8. You all follow me in this class? Everybody with me? Now the next thing I look for is that plotted on the Smith chart. Some people didn't number their points, and frankly, some people I don't think understood this problem. If I don't see the numbering correct, I can't really give you credit. I have to understand where you came in at, what you're doing. So for the Smith chart over here, and again, this is wide. And let's put this in the center. So here's the one circle, as such. And 0.25 plus J18. Well, 0.25 is something like that. And that's 0.25. And then 1.8 is about here, I think. J 1.8. So if you look at this where these two lines intersect, about here, this would be ZL. Again, and that would be 0.1 that I look for. You all with me? Now, we're doing a shunt. It means it's in parallel. You all with me? So the next thing you do is take your compass and you draw this. Maybe I should get a different color, but I think most people have an idea what I'm doing right here. I'm just trying to show you this is going to be a constant deflection coefficient circle. That's the next point I go to is YL. Everybody follow me? Plus, right? That's just 1 over ZL. That's going to be right through here. And that's YL, that's 0.2. Now, after that, before we do, yes, sir?
I think it's 0.5.
You're right. It is. It is. My bad. 0.5. Okay. 0.5. I'm a little under the weather, and I haven't sleeping very good right now. But so this is 0.5. I'll put it. It should all be up there. This is 0.5. You're absolutely right about that. Now after that, since this is 0.2, we know we're going to start here, and there's going to be something wavelengths towards generator here that we'll get in a second. Everybody follow me how I got this so far? Next thing I have to take a look at, we want to minimize this, and that's an open circuit stub, right? This is where people, I think, made the mistake. So if you have an open circuit stub, as such, if you look at this, the load impedance is equal to infinity. The normalized load impedance for this would be for the stub, would be equal to infinity as well, and that means Y stub would be equal to 0. Does everybody follow me, class? How many do? All right, this is where people made mistakes. For some reason, they used a short circuit stub, not an open, or at least that seemed to be the case. Now here, if you have this Ys equals 0 after it's normalized, that's at this point. Did everybody follow me? Right? Now, we want that minimum. So if you think about this, when I'm moving this way, I'm hitting plus J something initially, not negative. Y'all follow me? If it was a short circuit stub here, it would be negative J something. Follow me, class? So if we want this a minimum, right, we want to land, when we want to move until we hit the 1 circle, but we have the point 1 minus J something. Y'all follow me? Let me see this right here, because if it's a minus J and you add a plus J something, it will mean this distance is smallest. How many understand that concept? You'll get another problem like this. Are you with me, class? All right. Find out where you make errors, because you'll see this again on the final. And I want to make sure that you understand the concept. If we want a minimal distance, the minimal distance starts positive, so we have to have, the thing we're going to add to it has to have a minus J sense to it. Y'all follow me? So that's this point. And if you shoot through here, can you just tell me what this is so I can look?
It's 0.423 lambda.
And this is?
That's 0.302 lambda.
Y'all agree, class? Roughly? So we're going to get the line, this length right here, the L through line, and that's going to be the point I landed at, which is, I'm going to assume it's about right. Is that right? About 0.032? Or 0.302, pardon me. 0.302, and I'm subtracting from that 0.423, approximately. Right? And then I have to add 0.5 lambda. So when all that's done, it's 0.3782 about. Everybody with me so far? And again, I'm just going to locate how long you have to, how far away from the actual load you have to be before you include the stuff. Now, over here, I have 1 minus J. What do you have for that minus J business? I put the answer. Huh? 2.6? About 2.6? 1 minus J, 2.6. Clear on this, class? Now, I have to move. If you think about this, here, when I have the open circuit stub, I'm coming in here, correct? And I have to move until I hit what? 2.6 here, right? So it should be out here, J 2.6. Does everybody follow me on this one? Why I'm moving in class? Give me a show of hands if you do. I want to make sure, because some people, I honestly, there were some people, I couldn't tell what you were thinking. I mean, I saw, it's very hard to grade something like this unless I have numbers and understand where you're going, the next step. So now you're just going to go from here to that point. It's less than a quarter wavelength, but greater, I mean, it's less than a quarter, but it's going to be greater than an eighth of a wavelength. So down there, I got a value. Well, tell me what you guys got, because a lot of people got that right.
0.197 for that 1 plus 2.
0. Would you say 192 lambda? I think is the correct answer, isn't it?
I thought so. 1.9.
All right, and again, some swap, different Smith charts, you're going to get different values, but I gave everybody that's doing this in the proper order full credit for this. I mean, where it's reasonable what you're doing. So this means this stub is 0.1192 lambda. And I've got the equations, but this is the technique that you'd use. Now, I want to just give you one bit of caution about this. On the final exam, I will give you either a series stub or a shunt stub, parallel stub, and it will be either open or it will be a short, and I'll ask you to minimize either the through line or the actual shunt line, the actual stub line. Y'all follow me, class? So know that's coming and prepare. And make sure you can't just know a little bit about it. I'm going to ask you this. You got to make sure you know all of it, all right? Okay? Do you remember we covered a problem just like this? Anybody on the board? Because I would. Okay. All right, next problem. Wasn't meant to be a hard problem. I think the biggest problem is right here. People assume there's a short for some reason, not an open. All right, next. I think this is the D field problem, isn't it?
Yes.
All right, so for this problem, you might as well just okay, for problem 2, I give you a value of the actual volume charge density as, tell me what it is.
1 over r squared.
Just 1 over r squared. And it's in nanocoulombs per meter cubed, right? And this is for r less than a, greater than 0. And rho v equals 0 for r greater than a. Y'all with me? Do you remember this problem on the board? Anybody? That's where it came from. So if I take a look at this, right here, we do first, the first is going to be for r less than a. And I didn't draw this up here, but basically what I'm going to have is this. If this is a, and if I have r less than a, I really have this. And so all the charge, I'm just trying to show this simply, right? All the charge inside there has to be, and this is what I look for, the integral of d dot ds over the closed surface has got to be q enclosed. That's what I was looking to see, something of that nature. Now, here, that's spherical, right? You could have written an integral formally and done it, but this is really just going to be the surface area, 4 pi r squared times d of r. And over here, it's the charge enclosed, correct? So if you look at that, now you can go ahead and do this. It's a triple integral of the charge density, which is 10 to the minus 9th. Get a different marker. 10 to the minus 9th over r squared, that's rho v, times the differential unit of volume, which is going to be r squared sine of theta, d theta, d phi, and we can go dr here, and you can prime that if you want. And here theta goes from 0 to pi, phi goes from 0 to 2 pi, and then r goes just from 0 to r, or r prime goes from 0 to r. I'm writing it down formally. It's shown in the answer. You all with me, class? This is just the total charge enclosed. Well, you see that these two r's cancel entirely, right? The r squared on the bottom cancels the r squared up top. You all with me, everyone? And if you look at this, when I do the integral of sine theta d theta, I get minus cosine theta evaluated from 0 to pi, which will be 2, and then I integrate d phi from 0 to 2 pi, which is going to be simply 2 pi, so I get 4 pi right here. And then when I integrate r prime from 0 to r, I just get r. You all follow me, class? So it's going to be r here And it is times 10 to the minus 9, right? Because it was nano. Correct, class? Can you all see it back there? Far back? All right. Now, I set that equal to 4 pi r squared d of r. And I can see the d of r itself, the 4 pi's go. And I'm left with 10 to the minus 9 over r. And that's going to be for r greater than, or I'm sorry, r less than a. And that should be in the solution. Do you all see this? And again, it's just a straightforward integration. The 4 pi's go away. Next, after that, when you're at r, for r greater than a, and you put this down, the integral of d dot ds over the closed surface is equal to the charge enclosed. Well, that's going to be another triple integral. And I'll just put it down this way. I'll write the whole thing in a second. dv. Well, this will become simply 4 pi r squared d of r. Same as before, it's just the surface area of a sphere times d of r. Now you're outside where the charge exists. And then on the inside here, you have to go ahead, and now you're going to go through everything. Here it's going to be 10 to the minus 9 over r squared. That's going to be times r squared sine of theta, d theta, d phi, dr. The only difference between this and this right here is now we're going to go to a, and that's where we stop. Y'all follow me? Some people, I think, made a mistake. So here, theta goes from 0 to pi, phi goes from 0 to 2 pi, and then r goes from 0 to a. Here you're going to get the r squareds again, so they're going to cancel. And when you do this, you're going to get 4 pi, right? And it's going to be times 10 to the minus 9 here. And then you're going to get, well, dr integrated is just r, then it's going to be times r from 0 to a, which is just going to be a. And that's equal to 4 pi r squared d of r. And therefore, d of r is equal to 4 pi's cancel, is 10 to the minus 9 a over r squared. And this is true for r greater than a or equal to a. And if you graph it, right here, you can see this particular one is coming in from infinity. Y'all follow me, class? Any indication is coming in from infinity because you have 1 over 0. This would be 0, and this is r. It's coming like this, and then when it hits this point, this is 1 over r, and this is going to be proportional to actually 1 over r squared, but it would have 10 to the minus, it would have the 10 to the minus 9 there. I just wanted to see some general indication how it's monotonically increasing all the way down. If you had that right, and you had anything that was reasonable over here, you got full credit. Y'all with me? Now, one thing I did want to say about this one that bothered me. I saw people, and I wasn't sure why, that had this. They had no D field, or R less than A. And you have to understand, you need to do this correctly for both of those regions. All right, it has to be that way. Does everybody follow me on this? Remember that problem basically being up there on your last quiz where I had a problem just like that, only I asked for the voltage? I didn't this time, because I didn't think there'd be enough time. But on the final, you can almost bet there'd be something with voltage related to something like this. All right, next. All right. Oh yeah. This is the inner and outer, the resistance between the inner and outer surface. So it's really a cylinder with an inner radius A and then an outer radius B. And what I want to know is the resistance, the equivalent resistance and capacitance per meter that would be between the inner and outer radius. This is a metallized region. I think the cylinder picture came through in pretty well. So y'all follow me on this, class? But it's per meter. So if we do, well, let me go ahead and do this. So the conductivity between these regions was what? Sigma naught over rho, is that right? And what was the permittivity? Was epsilon naught times rho, correct? So again, just a function of rho. Anytime you have that, you know you're going to do integrations. And I do these, you can almost bet something like this, either spherical or cylindrical will be on the final, something like this. So if you look at this, we'll do resistance first. So if we're after resistance, first thing we do is assume I. And that I will be, if I look right down the z-axis, the I is coming in here, and that means there's going to be a current density J that's going to be spread out radially. It's going to just go from the inner surface to the outer surface. Do y'all follow me in that, class? And in general, you can think of it this way, that the integral of J dot ds over the closed surface is really going to be the I penetrating that surface. So if I try to do this, if you went out here and you just showed something like this, it's all the current that penetrates radially outward from the inner to the outer surface, if you're assuming that current. Y'all follow me on this one, by the way? Right? Okay, now, that means J will be I, and it will be divided by the surface area. That's the outer perimeter, or 2 pi rho, divided by the height, which is 1. I left h equal 1 because I want it per meter. Does that make sense to everybody? All right. So we have J, and it would be in the A rho direction. From there, we get E, and E is J over sigma. So here, I have that, I over 2 pi rho. And now sigma is sigma naught over rho. A rho. So that's simply I over 2 pi sigma naught A rho. And this would be volts per meter. That's a constant. Y'all follow me? After that, you get the voltage. That's the E field to get the voltage. I'm going to integrate E dot dl. At this point, I'm going to go from A to B, but you can see that's a constant value. If you integrate an electric field, that's a constant over any difference in distance, over any distance. It's just the distance times the value of the electric field. How many understand that? Are you with me? Right. So, and I told you, fundamentally, we could put D rho down here. I think it is shown up. We could put D rho down here, A rho. And we could put E field as that dotted, and you're going to get the same thing. You're basically going to get I over 2 pi sigma naught here, and then it's going to be times B minus A would be the voltage. And finally, to get the resistance, you take that voltage and divide it by the current positive. And that means the resistance is going to be V over I. So here it's going to be B minus A over 2 pi sigma naught ohms. Again, I left this in terms of B and A and sigma naught. There's the first part where you just showed me the formula that you figured out through your reason. Right? And then you put in the values, and I gave you sigma naught, B I think was 3 centimeters, A was 2 centimeters, correct, class? And at the end of the day, when you put that in there, what do you get for this? I've got it over there. What was it?
0.531 million.
That's right, 0.531 milliohms. So that was the resistance when you plug in the values A, B, and sigma naught. Correct, class? And again, it's just plugging and chugging. But sometimes when I see formulas, well, this to me seems pretty straightforward, but I see forms of the formulas that I don't understand how in the world you got. You got like A squared and B up. And so I know if your formula is correct, the answer will be right. And so I'm trying to always ascertain that. So the next part was the capacitance, and I'll do that over here. And for the capacitance, we start by assuming a charge per unit length QL, then we get the D field. Now again, the D field is just going to be the charge over the surface area. Again, this is cylindrically symmetric, so it's going to be like the outer wrapper of a can. Be 2 pi rho times the height would be the area, so it's QL over 2 pi rho, A rho. Then we need E, right? To get E, we go ahead and we take that, QL over 2 pi rho, and we divide by epsilon, which is epsilon naught rho. Or we get QL over 2 pi epsilon naught, and this becomes rho squared A rho. Everybody with me, class? And again, I'm just methodically going through it step by step. And this is, by the way, this is what I was looking for, these steps sequentially, so I could see what you're doing. And then finally, to get the voltage, you can put minus the integral, the E field dot DL. Really, you can use absolute value, it won't matter. So this is going to be the integral of QL over 2 pi epsilon naught rho squared, and then it's going to be A rho dot A rho is 1, so it's D rho. And that means I get QL here, 2 pi epsilon naught, and then I get 1 over minus 1 over rho, so it's 1 over A minus 1 over B. And finally, the capacitance is equal to Q over V, and it's that divided by V, so it's going to be 2 pi epsilon naught over 1 over A minus 1 over B. And this is capacitance per meter. And a form like that, I mean, some people put everything, they just left everything 1 over everything there. That's fine as long as QL wasn't there. And when you do that, what do you get for the value capacitance? Anybody? Say again? That's right. 3.33 picofarads roughly. And the exact value is on the solutions. With me, class? And try as best you can when you get problems, for future problems, to always show me the steps, like from here to here to here, and then the voltage. Because sometimes the only thing I see is a voltage and it's wrong, and I see the answer and I can't give you any points. Really, I tried. Okay. Finally, last problem is just 3 different charge configurations, and I want the total electric field from them. And this is just making sure you understood the basic, I guess, the electric field mapping from either a line charge, point charge, or surface charge. And for that one, let's see here. So here's X, here's Y, here's Z, and we got point charge of 6 microcoulombs located at 0, 0, 1. So that means I got a charge here at a height of 1, and I'll just call that Q1. And then I have a line charge of 180 nanocoulombs per meter along the x-axis. So then I have this charge is right there. And I have a line charge on the x-axis of rho L. I'm going to leave it as rho L for now. Everybody follow me? Try to draw them out. It'll help you. And finally, I have a sheet of charge at c equals -1. So that's in the xy plane. So I have a sheet of charge down here. Right? And this has got a value right here of rho S. And then we want the electric field at position 152. So it's x equal 1, that would be here, right here, y equals 5, and z equal 2. And I want E. Can y'all follow me, class? I'm just trying to draw this up so you can get an appreciation of what we're after. We're after the field there, which will be the sum of all the field components. Y'all agree with me? So if you look at this, first the electric field from this sheet of charge is going to be in the positive z direction. Do y'all agree with that, class? Right? So I can say, and I'll take this electric field E from the sheet of charge, or from rho S at that point, is going to be equal to rho S over 2 epsilon naught in the AZ direction. That would be the electric field from the sheet of charge at that point of observation. Does everybody agree with that? All right. Next, we'll get it from the line charge right here. For the line charge, if you think about this, it doesn't matter with the x positions, does it? If you look at the x position, it's up and down the x-axis, right? So if I look right down the x-axis here, and I have rho L, I have to go out y equals 5 and then z equal 2. Do you agree with this, everyone? So I come out, I go down a distance of 5, and then I go up a distance of 2. And now I want the electric field from this line charge, rho L. Now, the way we talked about this, to get that line charge, I'll put it over here. Remember, rho L, E, the electric field from the line charge, rho L, is going to be equal to the charge density, since it's infinite, rho L, over 2 pi epsilon naught, and it's divided by rho, and then a rho. Do y'all remember me putting that down? Now, what we need to do is get a rho correctly. First, if I look at this, this would be rho vector here, right? From here to here. So if I write that, rho vector would be equal to, as far as this goes, it's going to be 5ay, right? And it's going to be plus 2az. Y'all follow me? And I'm just putting down what the vector would be from the point, from the x-axis to the point of observation of the field. X has nothing to do with it. Can y'all visualize this? Now, if I have that, next, I need to get the magnitude of rho. And the magnitude of rho here is just going to be square root of 5 squared plus 2 squared. Y'all agree with that? Now, to get a rho, that's going to be simply rho vector over magnitude of rho vector. Agree, everyone? That's a unit vector in the direction from the line charge to the point of observation of the field. So over here, you can put the values in a second, but this becomes simply rho L over 2 pi epsilon naught. Then I have rho, which is that. And then it's times a rho, which is going to be 5 plus 2, 5ay. This is actually the square root of 5ay plus 2az. But it's divided by the square root of these numbers squared. So this is actually the value you're going to get. And it has 2 components. Remember, normally this would be 5 squared plus 2 squared to the 1/2 power. But because of this unit vector, it's divided by that to the 1/2 power. It really becomes just a single power. Do y'all follow me, class? So that's the second part. Finally, for the point charge at this point, if you look at this, the E field from the point charge at the point of observation, well, it's always going to be Q over 4 pi epsilon naught r squared magnitude, right? You might as well get this. If you look at this, I may if you look at this, this is r vector from this point where the charge is. Do y'all follow me? So if you got r vector from that, that's the point of observation. I mean, the x coordinate here is 0, right? And the x coordinate there is 1, right? So you're going to have difference in the two. You're going to have 1ax. Then you're going to have a difference in y. Here, y is 0, correct, class? That is 5, so it's plus 5ay. And finally, for z, it's 2 there, it's 1 there, so it's plus just 1az. And that would be our vector. Do you all agree with that? I think some people kind of fumbled some of these just because I think they're trying to hurry through it. But if you look at this, therefore, now I put it as Q over 4 pi epsilon naught. Here, I can take r squared, or I can take r magnitude actually. And that's the square root of 1 plus 5 squared plus 1. Then I can make this, normally it would be r squared, and but then I'm going to have an AR here, so it's going to be this to the 3/2 power, so that's 25, 26, 27 to the 3/2 power. And then I have to multiply by r, which is going to be 8x plus 5ay plus az. And now I get the values for that one. And again, you're going to put the values for charge in there and different things. But this is the process. Then you have to add them all up. And you can see I have one component contributing to AX here. And then for AY, I have 2. I have this and this. And for AZ, I have 3. I have that plus that plus that. Y'all with me, class? So if you do that, and I have the answers down there, it's plugging and chugging. And they should be up there.
I still wrote down all my equations.
What's the final answer for that? When you add them all together? Isn't it on one number or not?
It is.
Can you give it to me?
384.9 in the AX direction, plus 2,483 in the AY direction, and then plus 2,000.
2,483?
Yes. 2020 in the AF in this AZ direction.
Yeah, and that's just bookkeeping, that thought. You have to be able to visualize this. And that was it in a nutshell. I always, on the final exam, I always give a problem where you have to know the electric field from the common charge distribution, sphere, line, and surface. But, you know, I don't have to put all three of them down there. It could be a point charge and a line charge or something like that. But make sure you know how to get them. That's it. All right. Any questions? I graded very, very, I guess, easily on a lot of this stuff because I think some people, frankly, I think some people are not. It wasn't meant to be hard. All right, if you got questions, so, maybe not. So have a good break, come back, and if you, for whatever reason, if you had a bad day, put it behind you, realize there's plenty left. You got a final exam, you got a lot of quizzes. Just figure out what you need to do and where you're weaknesses. I try to make this fair. It's actually, there's a couple of older